Good day, class. So today we will be discussing about precipitation. So we all know that precipitation is part of the hydrologic cycle. But first, let us define what is precipitation. So precipitation is water released from clouds in the form of rain, freezing rain, sleet, snow, or hail. Precipitation falls as rain. It is the primary connection in the water cycle that provides for the delivery of atmospheric water to the earth. Precipitation is also defined as liquid or solid condensation of water, water vapor falling from clouds or deposited from air onto the ground. Precipitation is measured as the amount of water that reaches horizontal ground or the horizontal ground projection plane of the Earth's surface, and is expressed as a vertical depth of water or the water equivalent of solid precipitation. Precipitation in the form of ice flakes, such as snow, is called solid precipitation, and that in the form of water drops is sometimes called liquid precipitation. How do raindrops form? The clouds floating overhead contain water vapor and cloud droplets, which are small drops of condensed water. These droplets are way too small to fall as precipitation, but they are large enough to form visible clouds. Water is continually evaporating and condensing in the sky. If you look closely at a cloud, you can see some parts disappearing or evaporating, while other parts are growing or condensing. Most of the condensed water in clouds does not fall as precipitation because their fall speed is not large enough to overcome updrafts which support the clouds. For precipitation to happen, first, tiny water droplets must condense on even tinier dust, salt, or smoke particles, which acts as a nucleus. Water droplets may grow as a result of additional condensation of water vapor when the particles collide. If enough collisions occur to produce a droplet with a fall velocity which exceeds the cloud updraft speed, then it will fall out of the cloud as precipitation. This is not a trivial task since millions of cloud droplets are required to produce a single raindrop. A more efficient mechanism known as the Bergeron-Findeisen process for producing a precipitation size drop is through a process which leads to the rapid growth of ice crystals at the expense of the water vapor present in a cloud. These crystals may fall as snow or melt and fall as rain. Now, you might be surprised at the number of gallons of water that fall from the sky in even a small but intense storm. Did you know that 1 inch of rain falling on just a single acre results in 27,154 gallons of water on the landscape? And have you ever wondered, what do raindrops look like? As Alistair Frazier explains on his webpage, Bad Rain, small raindrops, those with a radius of less than 1 millimeter, are spherical, like a round ball. As droplets collide and grow in size, the bottom of the drop begins to be affected by the resistance of the air it is falling through. The bottom of the drop starts to flatten out until at about 2 to 3 millimeters in diameters. The bottom is quite flat with an indentation in the middle. Much like a hamburger bun, raindrops don't stop growing at 3 millimeters though, and when they reach about 4 to 5 millimeter, things really fall apart. At this size, the indentation in the bottom greatly expands, forming something like a parachute. The parachute doesn't last long though, and the large drop breaks up into smaller drops. Precipitation rates vary geographically and over time. Precipitation does not fall in the same amounts throughout the world, in a country, or even in a city. The map above shows average annual precipitation in millimeters and inches for the world. The light green areas can be considered deserts. Have you ever watched a raindrop hit the ground during a large rainstorm and wondered how big the drop is and how fast it is falling? Or maybe you've wondered how small fog particles are and how they manage to float in the air. The table shows the size, velocity of fall, and the density of particles or the number of drops per square foot or square meter of air for various types of precipitation, from fog to a cloudburst. Instruments for measuring precipitation include rain gauges and snow gauges, and various types are manufactured according to the purpose at hand. Rain gauges are classified into recording and non-recording types. Non-recording types include cylindrical and ordinary rain gauges, and measurement of precipitation with these types is performed manually by the observer. Recording types such as siphon rain gauges have a built-in recorder, and the observer must physically visit the observation site to obtain data. As rain gauges measure the volume or weight of precipitation collected in a vessel with a fixed orifice diameter, the size of the orifice needs to be standardized. Cylindrical rain gauges and ordinary rain gauges. These instruments work according to a simple principle of measurement and also have a straightforward structure. They offer the advantage of having a low rate of problem occurrence. Cylindrical rain gauges. As this type of rain gauge can also be used to measure snow, it is alternatively known as a cylindrical rain or snow gauge. It consists of a cylindrical vessel with a uniform diameter from top to bottom and an orifice at the top. It does not have a funnel. Rainwater enters through the orifice and accumulates in the cylindrical vessel, which is weighed at regular intervals with a precipitation scale. As the amount of precipitation is determined by subtracting the vessel weight from the total weight, the dry vessel is weighed before observation. Ordinary rain gauges. Ordinary rain gauges are the type used at non-automated observatories. With such devices, the observer takes measurements using a rain measuring glass at regular intervals. This type of rain gauge consists of a receptacle, a shell, a storage bottle, a storage vessel, and a rain measuring glass, which is a measuring cylinder graduated in precipitation amounts based on the diameter of the receptacle's orifice. The shell acts as a container for the storage bottle and the storage vessel. The storage vessel is a cylindrical metallic container that houses the storage bottle. The measuring cylinder, as shown in Figure 6.4, is transparent and graduated in units of precipitation. Rainwater entering through the receptacle accumulates in the storage bottle, and the precipitation amount is measured with the measuring glass. Rainwater entering through the receptacle accumulates in the storage bottle, and the precipitation amount is measured with the measuring glass. Rainwater that overflows from the storage bottle enters the storage vessel. The amount of overflow is also measured with the measuring glass and is added to the amount of precipitation in the storage bottle. Siphon rain gauges. A siphon rain gauge enables automatic, continuous measurement and recording of precipitation. This type of rain gauge consists of a receptacle, as you can see from Figure 6.5, to measure and record its amount. The measuring part consists of a float with a recording pen attached, a storage tank with a siphon to drain a fixed amount of water, and a clock-driven drum. Rainwater gathered by the receptacle is led from the rain receiver to the storage tank through an adjustment vessel. As a result, a float in the storage tank moves upward. A recording pen is connected to the float. When rainwater in the storage tank reaches a level equivalent to a fixed amount, it is drained by the siphon. This procedure is repeated as long as rainfall continues and the pen repeats traces from 0 to the maximum on the recording paper. When the rainfall stops, the pen traces a horizontal line. Tipping bucket rain gauges. This type of rain gauge generates an electric signal for each unit of precipitation collected and allows automatic or remote observation with a recorder or a counter. The only requirement for the instrument connected to the rain gauge is that it must be able to count pulses. Thus, a wide selection of configurations and applications is possible for this measuring system. Solid precipitation can also be measured if a heater is set at the receptacle. This type of rain gauge consists of a receiver and a measuring part, with the receiver serving as the container for the device, as shown in figure 6.8. The measuring part consists of a tipping bucket and a pulse-generating reed switch or mercury switch assembled within the receiver. The tipping buckets consist of two triangular vessels attached to the left and right of a rotation shaft, each with a capacity equivalent to a specific amount of precipitation. The reed or mercury switch is connected to these tipping buckets to generate an electric signal each time the buckets tip. That's why it's called tipping bucket. Analysis of rainfall data. Before using rainfall records at a station for any analysis, the data has to be checked for continuity and consistency. Missing rainfall data can be estimated using the rainfall data at neighboring stations. Now, how do we present rainfall data? We can do this in two ways. The first one is using a mass curve of rainfall. It is a plot of accumulated precipitation against time, plotted in chronological order. It gives information on duration and magnitude of a storm, intensity at various time intervals in a storm, slope of the curve. So when you try to see or try to look at the slope of the curve, it shows the intensity at various time intervals during a storm. The second is using hyetograph. It is a plot of rainfall intensity against time interval, and it can be derived from the mass curve of rainfall. It is represented as a bar chart, and it is useful in developing design storms to predict extreme floods. Mean precipitation calculation over an area. The methods used to convert point rainfall values at different rain gauge stations into an average value over a catchment include arithmetical mean method, Thyssen polygon method, isohyetal method. When we use arithmetical mean method, it's just simple as getting the average. So we have here P1 plus P2 plus P3 plus so on and so forth all over n, or simply 1 over n summation of P sub I from 1 to nth value. So P there is the average precipitation over the catchment area for a specific given time period, and P1, P2, P3, Pn are the precipitations in a given time period at stations 1, 2, 3, and so on and so forth, respectively within the catchment. So, when we use arithmetical mean method, think of it as computing your average grade. So, for example, you have a grade in algebra or geometry, trigonometry, and calculus, and you want to get your average grade. So, since you have four subjects, you simply add the 4 subjects grade, divide by 4. So that's how arithmetical mean method works. Thyssen polygon method. This method is considered superior to the arithmetical averaging method or mean method since some weightage is assigned to each rain gauge station. Even rain gauge stations located outside the catchment are used in computing mean precipitation. Using Thyssen polygon method, the rainfall recorded at each station is given a weightage based on the area closest to the station. Consider a catchment area with, say, 3 rain gauge stations. Let there be 3 stations outside the catchment, but in this neighborhood. The catchment area is drawn to scale and the position of these 6 stations are plotted on it. These 6 stations are joined so as to get a network of triangles. Perpendicular bisectors are drawn to each of the sides of these triangles. These bisectors form a polygon around each station. If the boundary of the catchment cuts the bisectors, then the boundary is taken as the outer limit of the polygon, and these bounding polygons are called Thyssen polygons. The area of these polygons is measured with a planimeter or by grid overlay. So to compute for the mean precipitation using piece and polygon method, if there are n stations with rainfall values P1, P2, P3, so on and so forth, and A1, A2, A3, and so on and so forth are the areas of the respective piece and polygons, the average rainfall all over the catchment P is computed as P is equal to P1A1 plus P2A2 plus P3A3 plus so on and so forth all over area 1 plus area 2 plus area 3 and so on and so forth. Or that is simply the summation from 1 to nth value of Pi multiplied by Ai over A, where Ai over A is called the weightage factor. And the last method is using isoheightal method. So let's define what is an isoheight. It is a line joining points of equal rainfall magnitude. The catchment area is drawn to scale and the rain gauge stations are marked on it. The recorded rainfall values for which a real average is to determine are marked at the respective stations. Neighboring stations outside the catchment are also considered. Taking point rainfall values as the guide, isoheights of different rainfall values are drawn, similar to drawing contours based on spot levels. And also, the area between adjacent isoheights is measured using a planimeter. To compute for the mean precipitation using the isoheightal method, if the rainfall values corresponding to the isoheights are P1, P2, P3, and so on and so forth, and A1, A2, A3, and so on and so forth are the corresponding inter-isoheightal areas, the average rainfall all over the catchment P is computed as P is equal to A1 quantity P1 plus P2 all over 2 plus A2 quantity P2 plus P3 over 2 plus and so on and so forth all over A1 plus A2 plus A3 plus so on and so forth, where A1 plus A2 plus A3 plus so on and so forth is the total area. This method is considered superior to the previous methods when the number of rain gauge stations are large. And that is it for today. See you on our next discussion.